Welcome to Coding Adventures. Today we're going to discuss about compression, and more specifically about a compression algorithm called Run-length Encoding, or RLE. And this will be a 2-episode kind of series. Today we're gonna see how to use this algorithm to compress and decompress text. Hopefully we'll be able to implement in JavaScript both a compressor and decompressor for some text. And tomorrow will be even more interesting because we're gonna use the same algorithm to decompress binary information containing an image that we're gonna display it on a canvas. Alright, so let's get started. Welcome back. So before we actually start and implement the run-length encoding algorithm, let's do a little bit of an overview of the compression algorithms. So I'm here on my notebook and I'm gonna write here compression. And in general, compression algorithms, they fall under two categories. They are lossless compression algorithms, and then they are lossy. And what this means is that this category of algorithms are algorithms where no information is lost. This is actually desirable, right? We have some sort of information, perhaps some text, we want to compress it, and when we decompress it, we want to get back the same information. However, and these algorithms are very important. However, more now than ever in modern times, these class of algorithms are actually very important, and they are powering the internet or multimedia world. These algorithms are algorithms with loss of information, but just tiny information that is probably not perceptible by the human senses. So what can you use basically this? Let's see some examples for both categories. Well, for the first one, you can use it to compress traffic, basically. So let's say you can use it to compress the traffic, maybe the HTTP traffic. The HTML pages that flow between server and client, they can be used to, they can be compressed using one of these algorithms to make them smaller and therefore get them faster on the client side. Or you can compress various files. You probably are familiar with the zip file format. You can basically archive some documents and then you unarchive them. And as I mentioned, it will be a shame if after compression you get corrupted data. So therefore, archives such as zip or perhaps RAR or 7-zip or even GZ file format, they are using algorithms inside that they are lossless, which basically that you don't lose any information. So therefore, lossy or lossy kind of algorithms are used usually to compress multimedia files. Files where you basically can compress them without perceptible degradation of quality. Imagine you have a music file, right? And if you compress it and if you ignore some frequencies, probably those very high frequencies or very low frequencies that are anyway not perceptible by the human ear, you can still get a very good recording. And this is actually used by algorithms such as, by the file formats such as MP3, if you know, music files, or by MP4 video files. All these will be very, very big if they are not compressed with one of these lossy algorithms. Or for images, JPEG, it's a highly compressed image format as well. However, not all images are compressed with lossy algorithms. For instance, if you are working with PNGs or perhaps GIF files or GIF files, these ones are actually lossless. And tomorrow actually we're gonna see how to uncompress some of these file formats, not PNG or GIF, but a more simplified one. All right, so therefore with this being said, this algorithm that we're gonna discuss today is called Run-length Encoding, or for short RLE. This stands for Run-length Encoding. and this algorithm falls under the category of the first algorithms lossless. All right, so perhaps it's now time to get started and make a plan for what we want to implement today. Let me put the notebook away and bring something else. And this is actually a file. This is a file, a binary file containing a message. And the size is 226 bytes. As you can see here, you can see it represented in hexadecimal formats, basically a bunch of codes. And if you're not familiar with hexadecimal, I have also a format, the same file represented in a decimal format. So the same numbers as before here, but instead of being represented in hexadecimal, these are represented in decimal. And I like hexadecimal because numbers align really nice on the screen. You can represent numbers from 0 to 255, basically a byte of information using just 2 characters. Anyway, this can be also formatted to look nicely on the screen, but nevertheless, we have the same numbers here. And there are 226 bytes. Since it says here bytes, it means that each of these numbers, they are in the range from 0 to 255, this being the biggest and this being the smallest. So there are 256 values for a byte, right? So this is an array of bytes, we can say, or it's a binary file. And we're gonna try to decode it. And we also, in order to decode it, or let's not say decode it, but actually decompress it, compressed files have an inherent property that they look encoded, but we're not talking about cryptography, just a little bit of obfuscation. So this is a compressed file, and we'll try to uncompress it. And we need to understand exactly how it's compressed in order to implement the algorithm to uncompress it. And the first hint I gave you before, it's compressed using an RLE algorithm. And I'm gonna give you a little bit more information in a second, actually. So let me grab back my notebook and see how this file is compressed. So before that, perhaps we should look this file. We should look at an ASCII table. I have here a copy of ASCII table. You may be wondering what we are doing with an ASCII table in an Unicode world, and you are right, but still for didactic exercises it's still pretty good. So ASCII table is used and was used more in the past to encode, to define basically a convention for encoding letters and symbols and numbers. And what is happening is that even the modern Unicode standards, for letters in the English alphabet, they kind of use the same encoding. But as you can see here, using this convention that was basically established by ASCII, each letter or symbol gets a code, right? Like these ones. All right, so keep this in mind. So we're coming back to the file here. And what I'll tell you is that some of these numbers are actually the codes of those ASCII characters, but not all of them. Because if it would be just that, it would be very, very simple to decode it. And we created messages encoded in the past just for fun, like under this format, right? We put jokes and then we provided a bunch of numbers and we said, these are just the ASCII codes, and just find out what is the message here, and you'll find out the answer to the joke. And if you want, you can refer to the video about Caesar cipher and strings here on this channel if you want to decode some of these old jokes. But nevertheless, today is not about only conversion from codes back to their equivalent character, but today we are talking about this run-length encoding algorithm. So looking back at this message here, as I mentioned, some of these numbers are actually the ASCII codes for particular characters, but others contains more information, contains how many times a character is repeating inside text. So let's do a little bit more baby steps and see how RLE, run-length encoding algorithms works in general. So first we're gonna take a general example, or we'll provide a general explanation, and then we're gonna go more precisely about our particular example. So let's switch here. So let's suppose we have a text composed of 3 letters or a few letters, A, B, C, C. This is our string, right? And we want to compress it using the run-length encoding algorithm. Well, this works by detecting if a character is repeating, and we can see already that A is repeating and C is repeating. So instead of just keeping the big text like that, we can say A2 or A3, meaning A repeated 3 times, then we can say B, and then we can say C2. All right? So now A3, it takes two bytes. Anyway, it's less than actually the 3 bytes here. But imagine we would have a bigger string such as A, 3, 4, 5, 6, 7, 8, 9, 10, and then a B. This string would have been compressed as A10 and B as a much shorter string. And of course, to decompress it, all you have to do is to find out this number here and then just expand it back into a bunch of original signals or symbols like that. So this is the basis of our of the run-length encoding algorithm. It's basically detecting if a character is repeating and how many times is repeating, and then storing that information, saying, okay, this character is repeating 3 times, and instead of the original sequence. All right, so this is in general. Of course, when we are looking here back at our message, we don't see exactly that kind of A3 as we put. These are codes. So we're gonna understand in a second how this is basically compressed. And actually that time is now to understand how we compress it. And that text, we know another information. It contains only ASCII characters. And an ASCII character, I'm gonna switch back. We're switching so many times back and forth, but we're gonna switch back to the ASCII table here. And we can notice that all ASCII characters, no matter if they are symbols or numbers or letters, you know, they are less than 126, even 127. So there are probably 100 something symbols here, which basically we can fit all of this in a single byte. Not in a single byte actually, but even in 7 bits in a byte. So with this being known, let's represent quickly here a byte. A byte is basically, by convention, a structure of 8-bit. Okay, so this is 1 byte. And this should be 7 bits until here. And with 7 bits of information, we actually can represent 128 values. Of course, with 8-bit, we can represent 256 values. And basically, since this text that we're trying to decode today contains only ASCII tables, they make use only of 7 bits of information. And because we know this detail, in the compression algorithm, we use the 8-bit here to signal if it's basically a character that needs to be repeated a certain number of times or not. So if it's 1, basically we'll have a certain encoding, or not. If it's 0, we're not repeating that one. In other words, basically for every number that we see in the file here, for every number that we see in this file, 13, 10, 165, 95, and so on, that number is basically, it's a byte, right? So can have the first bit either a 1, and then the rest of 7 bits here will represent the actual character. And if the first bit is repeated, it's 1, then in that file, for sure, and 160 is actually a number greater than 128, so basically has that bit set. The next number after, it's a repetition. So the next number after this one is the repetition. How many times a character should be repeated. However, if the first bit is 0, and then we have the actual character, this character is not a repeatable character. So these are the convention actually used by this encoding. Inside this file there are numbers. If the numbers have the first bit set, like this one, if the numbers have the first bit set, then it means that the second numbers following that one, it's a repetition. So here, for instance, we see a 160. We need to turn off the first bit to find out the character, and then 5 means this character contains in the 160 is repeated 5 times. So we are looking, when we're gonna decode the file, we're gonna look first of all for numbers that are bigger than 128. Because in the moment we set the first bit to 1, this whole number becomes greater than 128, right? Because 1, 0, 0, 0, 0, 0, 0, 0, a number with zeros after that, but the first one set, it's equal to 128. So whatever we put here after, it's obviously greater than 128. So we're gonna scan the file number by number. If it's less than 128, we just convert the code back into the ASCII code. However, if the number is greater than 128, we're gonna take it together with the next number. We're gonna extract from the first one the character, and then we're gonna repeat it how many times shows here. And we can see here a couple of sequences like this one actually. It's 160 here, 223 here, 160, 12. So this should be together. 95, it's alone. 107, 95, 13. Okay, again 160 and 4. So okay, so we're gonna proceed with this scanning of the file, and as I mentioned again, we're gonna find for each number what is the actual character and how many times is repeated. If we find it less than 128, this particular scenario, we know for sure the character is corresponding to code 13 and the repetition count is 1. If it's however 160, we're gonna find this character, we're gonna extract it, and then the repetition count in this particular case is 5. Is the second one. And then so on and so forth. So in this way, we're gonna expand all this binary file and find out the actual message inside. What a lengthy explanation. I kind of dabbled all over the place. However, let's hope this makes more sense once we go into the code here. I'm starting the code editor, and we need to implement the program. We know we need to bring here into the code editor first that file, and actually I have it here. We're not gonna work with binary files today. That would be nice, I guess, but perhaps other time. But for now, let's say we have this one as some sort of a constant, right? Bytes. And these are our bytes in that file. If we work with binary files, we can open the file in a binary mode and you can read byte by byte from a stream and so on and so forth. But for now, for simplification, we just read all the bytes in an array. And now we have an array of bytes, and now we have to decompress it basically and see what's inside here. So let's write a function basically, decompress, that will take as an argument an array of bytes. We're gonna pass the same one, and this one should return back the text, right? The decompressed text. So it's a particular function. So let's say here extract, all right, the 7-bit ASCII text by decompressing the bytes. And we're gonna put also here what is the format of the bytes. It's basically we have the first bit set to 1, and then we have 7 bits of information. Let's say 1, 2, 3, 4, 5, 6, 7 bits of information. And this is basically in case that it's something that is repeating, and then we have here 8 bits of repetition. So the other byte 1, 2, 3, 4, 5, 6, 7, 8. All right. By this format, we already can see that the next number here can be up to 255. So basically we can have a symbol repeating 255 times inside here. And then if there is a not repetition symbol, we have the first symbol, the first bit 0, and then we have the 7 bit of ASCII information. Okay, so all we have to do right now is to basically scan through all the bytes in that we receive as an argument here, and determine if the first bit is set. And if it's set, extract this information, and then read the next byte after to extract the counter, how many times this is repeated, and and then somehow multiply that kind of byte. And if it's not, we'll just put it as is. So let's implement first a loop on this byte array for let I equals 0, I less than bytes dot length I plus plus, just like this. And let's take in a variable. Byte is actually bytes of I. Let's call this function. Let's say we call it txt equal decompress of bytes. And let's print the text. We're going to use the println function that is available here in the environment, but if you're using other environment, you can use console log or something similar. Println txt. All right. Now our function will not do anything. So let's return some information. Let's make sure that is wired up correctly. It is. We'll see later on what to return from here. So we are scanning all the bytes, and we said, okay, let's verify if the byte is greater than 128. And why greater than 128? Because this is the easier way to check if the first bit is set. All numbers with first bit 1 are numbers that are greater than 128. An alternative to checking if it's greater than 128, we can create a mask, a binary mask, and we can use the AND operator, bitwise AND operator, apply the mask, and then compare if that one is greater than 0. But anyway, for now we're gonna just use the comparison with the 128 since it's very easy to implement it. So let's say if byte is greater or equal than 128, it means we are on this scenario here. We need to extract the 7 bit, and then we should read the next byte after, like this 5 here. So how can we extract the this 7 bit? Very simple. Byte, we subtract from it 128, right? So we subtract 128, so we should end up with just this one. All right, so so we have now the actual byte, which will be a code. And now, and we'll convert this back to ASCII later on, but now we have the code. We need to look into the counter. What is the counter? So the counter, how many times this byte is repeating? It's bytes in the original array from I plus 1, right? Is the next position. And if it's not repeated, let's have this variable defined here, count is 1. We assume that is not repeating, so count is 1, but if it's greater than 128, we're gonna read the actual counter, which is basically, maybe we'll read this 5 here. And now, not only that we read this one, but we have to advance the I. So remember, let's say we are on the 160 position here. We need to jump on this one, so we have to do an I++. So maybe we should increment here, maybe I++, and then we read bytes of I, which is basically from the next position. And notice here that we incremented I outside of actually 4, which is also perfectly fine. You can do that in JavaScript as in many other languages. So we are moving the pointer which is I, at the pointer to the current element. We are reading the count. We have the byte read. We have the count read. We're in good shape actually, because if basically the byte is not, if it's less than 128, is the default here. We read the byte. We assume is repeating just once. And this is exactly what we are on this second situation here. However, if the byte is greater than 128, we actually remove the first bit here and we read the count. So we're in good shape. Let's try to convert now to find out what is the actual character here. And I'm always kind of forgetting this in JavaScript, but hopefully we have this cheat sheet here with this snippet. So actually is this one, to convert from a code to the actual character. We use string from code point, and this is working, although this is a Unicode method, is working because the ASCII characters are falling on the same code points as with basically Unicode characters. So from with the Unicode code points, not characters, from char code, and we pass the byte. At this point here, we should get basically the character, the actual character, and we have the other piece of information, how many times we should repeat it when we display it. So, but we are not displaying it in this function, we are returning it. So perhaps we should have a text variable here, which is an empty string, and now, which is like some sort of a buffer, and each character we're gonna put it in that buffer, something like txt will add the character, but not only once. Actually, we should do it multiple times. We should do it as many times as the count says, right? So let's have a variable here, j, another generic index for 4, and j less than count, j++, and now we basically put inside the buffer that characters as many times as the count says. So count is 1 for all the regular characters, or not, if not here, we are reading it from the second byte. So to me looks correct. Perhaps we should just return it outside 4 after we finish all this operation. Before we close the function, let's return the text. All right, so that's all it takes to implement the Run-length encoding. Let me save it. ASCII, RLE. I'm gonna save it. Let me share this one with you on the chat, and then I'm gonna try to run it. Let's see if it's working. And I'm gonna run it. It's working perfectly fine. So what we see here on the screen is actually text, right? It says JavaScript, but this text is actually made up of all sorts of characters like pipes, underscore, slashes, backslashes, comma, and so on and so forth. Nevertheless, these are perfectly normal symbols in the ASCII table. We can find them somewhere around these codes here. We don't have any letter or number inside this one, but this is anyway, it's just the valid text, the valid ASCII text. It's actually what is called an ASCII art, and some people spend great amount of time designing this kind of images using characters. I generated this one automatically using a free tool on Linux, but anyway, that's beyond the point. So we got the text. Let's try to compare it with the original. So in the original one, we saw that it contains 226 characters. Actually, let's display them here. So we have the original one, bytes.length. Let's put here compressed. And now let's put here extract. Okay, uncompressed. Uncompressed is basically txt. Let's see how many characters there are inside here, which basically they're same as bytes because they're ASCII, and we can fit one ASCII character on one byte. And if we'll run it, all right, so we can see about 30% compression rate, I guess. 226 there in the original one and 315 in the expanded one. And perhaps we got this good compression rate because if I'm using my mouse here to select, I see a lot of white spaces, even here these characters are repeated inside here and so on. So we get a pretty good compression rate basically. All right, so that was the compression. It seems that it's working fine, and it's just a few lines of code. I hope that you are liking it, but let's not end the lesson here. Let's try to do also the opposite of this one. Let's see if we can create a function that actually compresses text. Should not be that hard, right? So let's create here in front of this one function compress. This time we're gonna take a text as an argument, and we should return an array of bytes, right? So the algorithms, okay, what algorithm we're gonna use in this case? Let me bring here back my notebook. We're gonna use the same compression scheme, but let's see how we're gonna work about this one. So let's take another text. We're gonna use, you know, symbols like A, B, B, C. Let's say we have this text. The way we're gonna do it, we're gonna scan it, obviously with a, we can use a for loop. We're gonna scan it with a counter I, and when we encounter the first character, we're gonna try to look if the other character is the same as this one, and if yes, the other character is the same, it's the same, it's the same. So we try to determine basically what is the character, which is A in this particular case, and how many times it's repeating. So it's repeating 5 times. And then we advance the pointer I here basically, and then we're going to determine that B is repeating 2 times, and then we're going to find C alone. So C is repeating 1 time here, right? So that is something that we can do pretty easily, I guess, right? So we're going to scan the text. We're gonna take one character and compare it with the next one, like basically with the I+1 character. And if we found it, we encounter the we increase that counter, or we can define a counter variable and we increase it. So let's not spend any more time talking and jump in the code here and try to implement this algorithm. So let's scan first the text for let I equals 0, I less than txt.length, and it's not recommended in general to scan the text like that, especially if it contains Unicode characters, but we know for sure that it doesn't contain Unicode characters. So we are good. So we are scanning this one. Let's read in a variable the current character. So basically it's txt of I. This is the one. And let's calculate also its code. Just to have it ready, because anyway we're gonna push in the destination the code and not the character. And for this one we're gonna use basically this other form is basically we're gonna say character quote point at 0. Okay, so we'll basically get with this one the code of that character. Character dot I said the char code at 0, right? So in this way we are getting also the code, because we're gonna use it later, right? Now, anyway, the main problem right now is to look ahead. We need to look ahead and determine if the next character, basically we need to determine if chr is equal with txt of I+1. Basically this is what I'm saying, look ahead. But not only for the next one, but look ahead multiple times. So let's put here a while actually in place. As long as this character is equal to the next one after that, so with the next one and the next one and the next one, we should increase a variable. So let's have a variable defined here. Let's say count is 1. Initially we assume that basically the character is not repeating, so appear just once. As soon as we basically found that it's equal to the next one, obviously count becomes greater with 1. And we need to do something else here. We also need to increase the pointer I, because otherwise if we are not increasing, this will kind of just check with only one character with the next one after. But if we are increasing it, we're gonna be able to scan multiple characters. So we increase also the pointer I pointing to the character. So that's it. after this while is finished, we should have basically in count how many times this code appears or this characters appears. So if it's not equal, we'll not hit the while loop at all. So we have the character appears just once. If it goes inside the while and the while does its job there, it basically will be able to find out that, okay, this character is repeating this many times. So we can say now if count, we determine that if count is greater than 1, let's copy this one from here, just have it handy, and put an information here, compressed and a 7-bit, okay, a 7-bit ASCII text using run-length encoding, and we'll compress it in this way. So if it's we encounter that the counter is greater than 1, let's basically encode this kind of sequence in the destination. And the destination, it's an array of where we're gonna push all these codes, which we have to define it. Let's have an empty array initially, and if count is greater than 1, what we are pushing the actual code, not the actual code, but code plus 128, because we want to, whatever code we find, we add 128 to set the first bit, and we are pushing something else as well. We are pushing on the next position immediately, we are pushing the counter. All right, else, if basically count is not greater than 1, basically counter is 1, we are just pushing the code. We are pushing the code, right? Just like that. We don't add 128 because we want to leave the first bit set to 0. And we finish the for loop and we are returning AR. That's our compress function. Looks pretty simple. Let's try it. All right, so let's have a text initially. We're gonna just say a this kind of 3 A's and 1 B. Let's have it a different variable, and then an array which is basically compress of txt, and let's print the array of numbers. Let me save it just in case I have an error. I don't want to lose the code. And if I'll run it, all right, I got some numbers, lots of numbers actually. Why I got, oh, txt2. I'm compressing txt2. All right. All right, so I got 225, 3, and 98, which I think it's correct. If I'm looking here, so I said A is repeating, right? So let's look at 98. 98 here is basically B, right? So B here is the, the third symbol, and here it should be A plus 128. So if we are looking, A is 97 plus 128 is indeed 225. So that one, A, is repeating 3 times and then is followed by B. So looks correct, at least at the first sight. Let's put more symbols here. Let's say we have A repeated 5 times, B repeated twice, and a C. We'll run it again. All right. So it's A repeated 5 times, then is B repeated twice, and then is C, which is 98. 99. The code of C is 99 if I'm looking here on the table. So we are in good shape. Seems that compress is also working fine. Let's give it a harder test actually. Let's not compress a dummy text like this one, but actually let's compress whatever we obtain by decompressing the bytes. So let me remove this one. All right. So at this point we are not invoking compress, but we have this text already. We obtain it by decompressing those bytes. Let's compress it back again and decompress it again. So, and then display it. And hopefully, if everything is correct, we should display again the same text. Okay, so let's say, let's bytes2 is basically we compress the txt. We compress whatever we decompressed. And now let txt2, we decompress it back. Decompress, we decompress these bytes, right? And now we can also, yeah, we can display it, or we can just see how it looks like. Let's run it. Oh, we didn't display it. Let's put print ln txt2, and if we'll run it, looks the same. So I guess our algorithms looks correctly here. And they are so simple. If we look to them again, they are so simple. What we can do, I mean, they are done, but what we can do at this point, perhaps we should put a little bit of more error handling inside. So I'm thinking, what about, let's say, in this text, we find a character such as, let's say at the end here, 160, which means, okay, we have a character, but then the file ends. We don't have how many times it repeats. It's something like that, just the file ends. It's a corrupted file. Yes, it is, but maybe we should handle that gracefully and we should not crash or something like that. So let's handle that situation first. All right, so here, if we encounter something, let's put a protection here. We increment I only if I less than basically bytes.length -1, right? Only then we increment and we read the count. If we still have bytes to read. If we don't have, we don't do anything. It's still working fine, but I guess this protection, it's okay. We can even test it. We can put back that one, but I guess it's okay. Let's see. Decompress looks fine to me now. Let's see for compress if we basically need to put any protection in place. Maybe yes, maybe not. Actually, we need. What about if we find a text, a character that is repeating, such as A, and is repeating more than 255? How many basically we can encode in the next byte? Then we'll have a problem. So what we can say, as long as we find a character and is the same as the next one, and count is less than 255, right? Only then basically we increase it, right? We increase it, count becomes 255, which is the last value. Only then basically we can increase it. And if we have a longer sequence, what should happen basically, let's say this is 500 characters here, right? So what will happen, we basically will encode it as two sequences, like A is 255 and A again appears 200 times, to say like that, right? Because in a byte we can put up to 255, we cannot put 455 here. So this protection is good and is actually quite logical for the algorithm, but I think we can also do a protection. We are incrementing I++ here outside of the for. We may risk going beyond the border of the file. So let's put the same protection that we put before. And if I is less than, in this case, txt.length -1, right? If we still have where to increment it, then we're gonna increment the counter and so on. So let's run it. It's working the same, but I think they are a little bit more robust if we put these protections. If we see other ones, feel free to add them here in the code. But basically with this, let me run it again. Yes, with this, I believe we achieved what we wanted to achieve for today, to decompress and compress a text file using the run-length encoded algorithm. We provided some explanations, perhaps too long explanations. But if you like this one, make sure that you watch also the episode from tomorrow. That will be a little bit hopefully more interesting. We're gonna try to decompress an image that is compressed with a similar algorithm and then display it on the canvas. All right, with this being said, I want to thank you for watching, happy coding, and see you tomorrow.